All right, so yesterday we finished off talking about how to choose an appropriate base, and in your pod you had to pick one for the molecule that was shown. Today we're going to talk about the other side of a running reaction, and that's picking an appropriate reaction solvent. If you think about the solvent for a reaction, what does it do?
Dissolves or pulls apart the molecule.
It dissolves your molecule, right? Ideally, your solvent's just the medium that your reaction takes place in, right? So let's make a note of that. Solvent is the reaction medium. And usually, your solvent is inert. What does it mean when I say inert? Non-reactive. It doesn't participate in the reaction in a direct way. Its bonds aren't broken in any way, usually. Let's take an example of an acid-base reaction, and I'm going to pick a solvent too. So in this example, our acid will be this ketone, also known as acetone. And I'm going to pick a base, so I'll pick sodium amide. And I'm going to run this in water. All right? So first thing I would do as a chemist is say, all right, in this case, this would be my acid, this would be my base, and water, I'm trying to use it as a solvent. If we look at the acid here, we've got a ketone. So let's go to our pKa table. And I'd say, all right, let's find a pKa of a ketone that looks like the one we have. If we look at it on the ketone side, we've got one where we've got a pKa of about what? What do you guys think? I would say that one with two ethyls on each side is a pretty close mimic, right? So do you guys see that? It's right. I guess I can't really show it with my marker here. But it's the one with the ethyl on each side of the carbonyl. It says about 19 to 20. That would be a pretty close pKa. So let's go ahead and write that down, and we'll say, all right, pKa of about 19 to 20. All right. And then we want to finish this reaction. Just one second. There we go. All right, so we're going to steal a proton from our acid. And ideally, what we want is to steal one of those protons. We would form ammonia in this process. However, does anybody see a problem with this? Water has a lower pKa than our acid, right? So if we think about water, what's the pKa roughly?
15.7.
Yeah, roughly 15.7. So we'll do pKa of 15.7. That means that instead of stealing the proton from acetone, it would prefer to steal it from water. So what I have drawn is actually incorrect. It wouldn't deprotonate here. Instead, we would form hydroxide. So we've run into a problem. We don't want to use a solvent that has a lower pKa than what we're trying to deprotonate. Than your acid of interest. Otherwise, you'll just deprotonate your solvent and your acid will be untouched. Instead, I'll show you guys a common example of a solution for this. In this example, we're going to use Acetone again. We're going to use sodium amide again. But this time I'm going to run this reaction in liquid ammonia. And if we think about this, right? Let's draw in these protons. This base will come grab this proton, pop electrons over here. We'll form our conjugate base that is resonance stabilized. We'll still have this sodium ion hanging around. And then our conjugate acid will be ammonia, and our solvent will be ammonia. This is kind of nice, right? Our conjugate acid in this case is the exact same thing as our solvent. We don't have to worry about removing it anymore. It's just going to go back into that bulk medium. So oftentimes the solution that chemists use when they're choosing a solvent is to choose a solvent that is actually the conjugate acid of your base. It just simplifies things. So chemists often choose a base whose conjugate acid is the same as the solvent. Makes sense, right? All right, if you guys go back to that table that I gave you, we've got this chart of common solvents in organic chemistry. These are the ones where if you were in a research lab, you tend to see them most commonly. It's not an exhaustive list. And you'll notice that I've got them in 3 different groups. The top group is polar protic. I list the pKa values. I've got polar aprotic next down. What do you think it means when I say aprotic?
The proton doesn't want to come off as easily.
Yeah, the proton doesn't want to come off as easily. If you notice, the pKa values jump up quite a bit as soon as you get to polar protic compounds. Or polar aprotic compounds. Specifically, if you look at polar protic compounds, what's special about all of them?
OHs.
Yeah, they've all got OHs, which means they can hydrogen bond. So polar protic compounds are normally ones that can hydrogen bond. Polar aprotic compounds are ones that don't hydrogen bond, but are polar. And then non-polar compounds, a lot of students will say, well, aren't there dipoles on some of them? Yeah, but they're just not very big dipoles. They're very weak dipoles. And these ones tend to have the highest pKa values of the bunch. It's always important that you choose a solvent that has a higher pKa value than the acid you're trying to deprotonate, but you also need to choose a solvent that allows everything to be miscible, meaning it's going to form one layer. That's also an important thing to remember. This delineation of solvents into polar protic, aprotic, and nonpolar will come back when we get into chapters 7 and 8, so you will refer back to this table later on, but it's pretty useful right now. Are there any questions with picking solvents? Yep.
What were you saying about non-polar ones? Why was it bad?
So nonpolar solvents, oftentimes if you're trying to do acid-base chemistry, you'll pick a nonpolar solvent. However, you need to make sure that the solvent you choose is able to dissolve the compound that you're trying to deprotonate, right? Otherwise, you're just going to form an oil-water interface. Good question. All right, there's one other acid-base theory that we've kind of left on the back burner. What was that called? Lewis. So Arrhenius is similar to Bronsted-Lowry. It talks about formation of hydronium or hydroxide. That's still movement of protons. But Lewis acid-base theory kind of goes on a tangent a little bit. So let's define Lewis acid-base theory. In Lewis acid-base theory, we're talking about movement of electrons, not protons. So in this case, do acids donate or accept electrons? Accept. So acids accept electrons. Bases donate electrons. The way I like to think about this is all of acid-base chemistry in this circle. Bronsted-Lowry acid-base theory makes up a small portion of all of the acid-base chemistry. So Lewis acid-base theory is actually more descriptive than Bronsted-Lowry. This is something that confuses a lot of people. It's a subset of Lewis acid-base chemistry. All right, so let's make a really generic drawing and we'll compare this. And it's going to look very familiar. In the first example, I'll have an acid, AH, and I'll have a base with our lone pairs. Let me move this. And we've got this equilibrium. We've got A as our conjugate base. And we've got our conjugate acid. Remember, with electron pushing, we start at the lone pair that's grabbing the proton. We grab that proton with the arrowhead. It's important that you have that arrow going the right way. And then this covalent bond is going to hop over to A. So if we think about this, B is donating its electrons, right? Its lone pair is being donated to that proton. That means that B is our base. And if we think about A in this example, it accepts electrons. So this looks exactly like Bronsted-Lowry acid-base chemistry. We're just thinking about it from a different angle. We don't really care about the proton. We just care about the movement of electrons. What's giving up electrons, or what's donating electrons, and then what's accepting electrons. However, there are some Lewis acid-base reactions that don't involve protons at all, and that's why we have this completely separate theory. So let's take an example of this. I've got ammonia, and I've got boron trifluoride. I'm going to draw it kind of in the plane, so that fluorine with the dash is going into the board, the one coming off the wedge is coming out of the board. If we think about the hybridization of this boron, what's the hybridization? Trigonal planar, right? So it's sp2 trigonal planar. If we think about the orbital that's left over, what's left over? P orbital.
Wouldn't it be trigonal pyramidal though?
Not quite, because there's no lone pair coming off of boron trifluoride. So if we think about the steric number coming off of that boron, it's only 3. Steric number of 3 is always going to be sp2. That means that we've got this empty p orbital just hanging out in a cloud above and below boron. Yep.
Is that fluorine on the bottom in the same plane as the other fluorine?
Yeah.
Okay.
Both, all the fluorines are... I'm trying to draw the boron trifluoride flat. We just can't really do that with 2D very well. So over here we've got this empty p orbital. That means that the lone pair on ammonia could be donated to that empty p orbital, right? So I'm going to draw those electrons going in. So if we think about this, this is donating electrons. Yep. Does that make it the acid or the base? The base, right? And if we look at boron trifluoride, it's accepting the electrons. It's going to be the acid. This is a really common theme in Lewis acid-base chemistry, is it's a lone pair getting dumped into a vacant orbital of some shape. All right, let's draw our equilibrium arrows. And then up here we've got a wedge and a dash. Looks like I'm missing some formal charges though. What's the charge on nitrogen now? Positive, and then on boron it's going to be what? Negative. All right, what this is called is a Lewis acid-base adduct. One interesting thing when you form these Lewis acid-base adducts is what's the shape of the boron now, or the boron side of the molecule? Tetrahedral. We went from trigonal planar to tetrahedral because we've increased that steric number around boron. So you can change the geometry of molecules when you do acid-base reactions. It's kind of cool that this is also a reversible reaction too. Occasionally, you might see it in other textbooks where instead of a covalent bond between nitrogen and boron, what they'll do is they'll show this as an arrow like that to indicate that this is a Lewis acid-base adduct. Usually the Klein textbook will just show a covalent bond though to avoid any confusion. But I did want to point that out in case you open up a textbook next year and you see something that looks different. All right, let's go review a little bit of some arrow pushing rules and some new nomenclature as well. Whoa. So if we think about this general reaction, come on, where we've got our base with its lone pair, got some electrons. This base, these electrons always will attack the proton. I saw a lot of people that were getting confused and they say, well, if we think about it, this proton is going to the base, so I'm going to draw it like that. It's not correct. You always want to draw it where the lone pairs are the source of your arrow, and then the arrow goes to the proton that those lone pairs are grabbing. If we think about the electrons in this covalent bond, those have to go somewhere, so these two electrons will end up getting popped over onto A. So we have to show our arrow pushing in the correct fashion. We've got A with a lone pair on it now, and a negative charge, and we've got HB plus. And if we think about the acid here, we could say by Lewis theory, that A accepts electrons. That means that this is a Lewis acid. And we said that B donates electrons. That means it's going to be a Lewis base, so I'll do LB. And then down here, I'm going to do the Bronsted definition. And in this case, we would call this our H plus donor. And this base is going to be our H plus acceptor. So I'll abbreviate this BA for Bronsted acid, and then BB for Bronsted base. Last but not least, I've got a new important term that's going to show up again and again and again. This is called nucleophile, abbreviated NUC, and electrophile, which is E+. In this case, if you think about the term electrophile, the suffix is phile, or the Latin root's philia. Does anybody know what philia means in Latin?
Like.
To like or love, right? So an electrophile is something that likes or loves electrons. If we think about which one of these is going to be the thing that likes or loves electrons, do you think it will be the acid or the base? The acid, because it wants electrons, right? If we think about the Lewis definition, we see that A is accepting electrons. That means it likes or loves electrons, right? So in this case, we will refer to this as our electrophile. And then nucleophile means something that likes a positive or partial positive charge. So if we think about B, B is going after H, or the proton, because it's got a partial positive. So we'll put this down here. This wants electrons. Our nucleophile is typically going to be a lone pair donor. And it wants delta positive or a full positive in some cases, and we'll see that later on in the term. So we've got three different ways to describe our acid and base. We can describe our acid as a Lewis acid or base, a Bronsted acid or base, or a nucleophile or electrophile. So we want to be very clear with this terminology. You can have situations where you only have a Lewis acid, but you will never have a situation where you only have a Bronsted acid, right? Because we know if you've got a Bronsted acid, it is also a Lewis acid. It's one of those weird examples. Did you have a question, or did somebody?
I was going to ask about that.
Yeah, so in this case, let's even make a note. Bronsted acids and bases are always Lewis acids and bases. But not the other way around. And that's something that tricks people up once in a while. All right, what we're going to do with the last chunk of time today is we're going to do a little in-class activity. Did everybody grab one from up front? This isn't going to be turned in at all. This is just simply questions like you might see on an exam or a quiz. And I want you guys to work together on this, so you're welcome to move around. First thing I want you to do is identify the acid and conjugate acid for each reaction. Then number two, I want you to estimate the pKa value for the acid and conjugate acid using the pKa table on the back. And then I want you to determine which side of the equilibrium predominates. So for example, you could use a reaction equilibrium arrow that looks like, that looks like this. Or you could have one that goes the other way that looks like that. I need you to help me determine which side is the predominant side of the equilibrium. And then include electron pushing arrows to show that proton transfer. So I'll give you guys a chunk of time to work on this, and then we'll talk about it as a class. Yep, this will go online. So let's take a look at the first one. We've got some acids in solution. Let me turn these down. I'll just do acid and base. This would be our conjugate acid, and this would be our conjugate base, right? If we think about the acid on the left-hand side, what's the pKa of hydronium? All right, negative 1.7. What about on the right? What's the conjugate acid pKa here? Negative 2.9. All right, that means that the conjugate acid on the right is actually a better acid, right? So the equilibrium is going to be pushed to the left or to the right? To the left. So we could show this with the reaction arrow. It looks something like that. That would be a good equilibrium arrow. Whoop. All right, let's go to the next one. We've got our acid and we've got our base. Over here we've got our conjugate base because it lost its proton. We've got our conjugate acid. All right, what's the pKa of our acid on the left?
9.9.
About 9. What about on the right?
15.7.
15.7. All right, so now our acid on the left is actually a better acid than our conjugate acid on the right. So equilibrium arrow-wise, it's going to be pushing towards that right-hand side. So it's going to be a lopsided equilibrium arrow. Let's keep on going down. Over here we've got our acid. It's still got its proton on. Amide is going to be our base. It's the thing stealing the proton. And then we've got our conjugate base, and we've got our conjugate acid. If we look at our pKa table, what's the pKa of the acid on the left?
19.2.
About 19.2, I think. And then on the right, what's the conjugate acid pKa? 38. So we'll plug that in and we'll say 38. All right, it looks like our acid has a lower pKa. That means it's more or less acidic. More acidic. So we're going to push this to the right-hand side. And a little bit like that. All right, the tricky one. We have to draw the anticipated products. So we've got two options, right? Let's draw out both options. Option one is where this is the acid and this is the base, right? So let's say we do that. That means that this oxygen would lose its proton and this would gain a proton. All right, option two is the other one where this would be the base and that would be the acid, right? So we can compare both of those. If phenol is our base, our conjugate acid would look like this. And our acid would look something like this. Which do you think looks more reasonable, option one or option two? Option one. So if we think about this, right? Earlier this week I said anytime you've got a conflict, look at your conjugate bases and ask yourself which one's more stable. So over here we've got our conjugate base. We've got our conjugate base here. This was our conjugate acid. This is our conjugate acid. So really what we're doing is we're comparing these two guys, our two potential conjugate bases. Why is the conjugate base from option one the better option? Resonance. If we have the Areo rules, it's a tie, right? It's oxygen versus oxygen for the atom portion. But then we go down to resonance. The conjugate base from option two has no resonance, but it does for option one. So I think we're in good shape there. So we'll plug these in. And then we'll go back and we'll add curved arrows really quick. But before we do that, I had somebody asking me about this where they said, all right, if we look at this last reaction, do you guys think we're going to get much acid-base chemistry that occurs? Is very much of that phenol, that compound on the left, is very much of it going to lose its proton? No. So let's think about this. The pKa of our conjugate acid here is about what? Does anybody have an estimate?
-2.
About -2. A lot of people are like, well, there isn't one on my chart. But we do know that there are some on your chart that have oxygen with a positive charge. Do you guys see those? Those were all ballpark of about -2, more or less. If we go over here and we look at the pKa of phenol, what's its pKa? About 9. So if we think about this, the conjugate acid on the right's way, 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 way more powerful. 10 orders of magnitude more powerful than phenol. So this equilibrium is almost non-equilibrium-like. It's only going to stay at that starting material side. Does that make sense? A little abstract to think about. So if we think about this equilibrium, really this equilibrium is so far that way, and just a tiny, tiny little speck that way that it's almost non-equilibrium conditions at that point.
I thought
Smaller pKa is stronger acid, right?
Yeah, exactly. So this is
because it's such a strong acid,
such a good acid. It's pushing so hard the opposite
It's gonna
direction.
give up- It's going to very readily give up protons.
Exactly.
Okay.
Yeah, it's going to more readily give up its protons. All right, I think that's where we're going to leave off. Remember, saplings due on Monday. We'll have quiz 3. And then a lot of people were asking about essential oils. They're not fully evaporated yet, so just wait until your next lab period to record the mass. It's okay.